Alright, here we are at section 3.2, logarithmic functions and their graphs. The idea for this section is that you should have already done the classroom activity, and these notes are going to be more of an extension of what you've learned in class. And when I say extension of what you've learned in class, you should realize that these two equations mean exactly the same thing. Alright? One is called logarithmic form, the other is called exponential form. They are essentially equivalent. So if I ever write anything, y equals log base anything of x, another way to rewrite that is going to be a to the y equals x. And again, if I write anything a to the y equals x, you can always reverse it and put it into log form. Alright, Alright, so here we have a couple straightforward, just want to practice a couple of transformations and making sure we can go from log form to exponential form. So here, if I evaluate f of x, this is log base 2 of 32, and I'm curious to figure out what does this equal. And there is no calculator button for this. This is something I have to know. This is log form, and if I change it over to that exponential form, I always say the base of my log is now the base of my exponent. So 2 is the base of the log. And then it's always 2 raised to what's on the other side of the equal sign. So that's the y, and I say equals 32. And well, now this is something I can figure out in my head. 2 to what power is 32? Well, that would be 2 to the 5th. So here, y is equal to 5. Right. I can do the same thing for g of x. G of x is located over here. We're looking here at log base 3 of 1 equals what? What we don't know, but again, we're in log form, and to solve this, we're going to put it in exponential form. So if I put it in exponential form, it looks like 3 is the base of my log. I'm going to raise it to my exponent, so I'm going to raise it to what's on the other side of the equal sign, and I say equals 1. 3 to the what equals 1? Well, the only possibility is that y equals 0. Alright, there are two very similar problems down here, h of 2 and j of 100. Why don't we have you try those, and if you have questions, we bring them to class tomorrow. Okay, so a couple calculator terms that we'll be using quite a bit. Whenever you say just log by itself, log is considered to be log base 10. Alright, but you're never going to write log base 10 because log base 10 actually means just log. Same thing for log base e. Log base e is known as ln, also pronounced the natural log. It's a lowercase l and a lowercase n for natural log. Alright, these buttons you've probably seen, you may have even used on your calculator before. Okay, a couple quick properties that I hope you would understand. If I have log base anything of 1, it will always be 0. Why is that the case? Well, for pretty much every one of these, you can prove it by going from log form to exponential form. So here, if I think the base of my log is the base of my exponent, I put what's on the other side of the equal sign as the exponent, and I say equals 1. Anything to the 0 equals 1. Well, that's true in exponential form. It's also true in log form. So it's really... that's our proof here. No matter what value of a, the log base anything of 1 equals 0. Here, same thing. The base of my log is the base of my exponent. Whatever's on the other side of the equal sign is my exponent. And then I say a to the first equals a. Yeah, that makes sense in exponential form. It also is a shortcut that we can use in logarithmic form. Log base a of a to the x is x. Well, here, if you think the base of my log is the base of my exponent, whatever's on the other side of the equal sign is my exponent, and I will say a to the x is the piece that gets copied over. And a to the x equals a to the x. No one would argue with that. All we did is write it in logarithmic form. So it's a nice little shortcut. If you have log base a of a to the x, it equals just x. Right, 2 more. This one's a little trickier because this is actually our exponential form. So we have to take exponential form and go to our logarithmic form. All right, so what does that mean? the base of my exponent is the base of my log. Log base A. The exponent goes on the other side of the equal sign, and then this x is what goes right here. Log base A of x is equal to log base A of x. No one would argue with it written this way. You can also simplify it down and just say, so, and what this rule is saying is that if you have log base A of x and log base A of y, well then these two x's and the y's are exactly equal. So let's quickly apply a few of these rules and show you how quickly they can go. Well, here's the application of the rule we just went through. Log base 2 of x equals log base 2 of 3. Well, there's only one possibility here. X has to equal 3. Log base 4 of 4 equals x. Well, anytime right here you have the same number, the log base 4 of 4 equals x, anytime these two are the same, your answer has to be, from our rule right here, our answer has to be 1. Okay, next, log base 5 of 5 to the x. Right here, we can simplify it down. You can see, same rule right here. We have log base 5 of 5 to the x. Well, that can simplify down to just x. And same rule we have here. You have 7 to the log base 7 of 14. Well, that simplifies down to just 14, using our little properties of logs. All right, so you're going to see this slide go relatively quickly because we've already graphed this. This is an exponential function. This is what we did last section. For your exponential functions, I will draw this one in red. The expectation that I would assume you have by now is that you know it has a y-intercept of 1. You know that this is going to have a horizontal asymptote going out to the left. And then as soon as it passes through 0, 1, it is going to start to rise very quickly. Well, from the classroom activity, I'm hoping that you saw the relationship between 2 to the x and log base 2 of x. The relationship between these two graphs is that they are a reflection over the line y equals x. So these two graphs are similar, but the idea here, the piece that I'm hoping we took away from class to graph logs, looking for a few important points. So I will take our log graph. I'll be drawing this in blue. What you're going to notice about a log graph is it is exactly the reflection over that line, that y equals x, which means instead of having instead of having a y-intercept here, we're going to have an x-intercept right here. We are always going to have an x-intercept of 1, 0. Instead of having a horizontal asymptote, we are going to have a vertical asymptote. As soon as we pass through this graph, right now it's rising very quickly to this point. As soon as we get to this point, 1, 0, the log graph starts to flatten out. And it is, for the most part, a very, and again, these are sketches. They don't have to be plotted with points. If you want to be super precise, you could plot more points. But essentially, there's just a few key points to logarithmic graphs. Like they're going to have an x-intercept at 1, 0. They're going to have a vertical asymptote at x equals 0. And as soon as they pass through 1, 0, they start to flatten out. They flatten out, but they do not have a horizontal asymptote. So when we graph our standard log, you're going to see, here we're looking, every log graph is going to pass through 1, 0, assuming it has no transformations. It's going to have your vertical asymptote right here. It's going to approach the vertical asymptote. As soon as it passes through here, it starts to flatten out. If I want to be super specific, this graph should technically pass through 1, 10. Oh, I'm sorry, 10, 1. Okay, so it's a quick sketch. All right, so to sum up here, our log functions, they have one vertical asymptote, they have one x-intercept, right? They do not have a y-intercept. And so they do not have a y-intercept as well as some people, you could say here, they do not have a y-intercept or a horizontal asymptote. Neither of those are going to be present. All right, but if you think back to your exponential graphs both had a y-intercept and a horizontal asymptote. So there's relationships here. Okay. Looking at your domain of a log function, if I go back to our graph, there are certain values we can substitute in. If you try typing in log of a negative number, your calculator is going to say error. In fact, even if you try to type in log of 0, your calculator would say error. There is no possible way to get an outcome over here. You're never going to get any outcomes there. So your domain, right? Your domain is x has to be greater than 0, cannot equal 0. The difference, if I go back, what about my range? What about my y values? This graph, while it starts to flatten out, it definitely does increase forever. So what that means is my range is going to be all real numbers. All right, you can only take the log of, well, what is this saying? Right here, you can only take the log of positive numbers. Another way to remember it, if you don't like saying x has to be greater than 0, you can only take the log of positives. All right, so we're going to quickly use our transformations to graph. This is a log graph that has a transformation that is 1 to the right. So I take my log graph. If I think of my standard log graph that we drew on the last slide, passes through here, vertical. All right, there's my standard log graph. All I have to do is shift everything 1 to the right, which means my my intercept, my x-intercept is here. My vertical asymptote has also shifted 1 to the right. And as soon as I pass through here, the graph starts to flatten out. So that green line will be here. Here's the same log graph. We'll do this one in a different color. Let's do this one in red. All right. G of x, that is a shift of 2 up. So let's go back. Focus on the blue logarithmic graph. We're going to take that blue log graph, and if I'm going to take that x-intercept, shift it 2 up. I can't really shift the vertical asymptote 2 up. It's still going to be in the same spot. So I know this looks a little tricky, but once I pass through this point is when the graph starts to flatten out very rapidly. All right, couple simplifications. These are rules we've done before. The easiest way to look at this is ln. So that's another way to think of that is log base e. And 1 to the e can be written as e to the negative 1. So what do we think that's going to simplify to? Well, using our rules from before, that's going to be just negative 1. You have the same 2 pieces here. That's from our log rules from a few slides ago. E to the ln of 5. Well, don't forget, e to ln stands for log base e of 5. Again, e to the log base e, well, that's going to simplify down to just 5. All right, so we have log base e of e to the 0. Well, think about e to the 0 for a second. Well, actually, log base e of e to the 0. Again, same thing. We have the same pieces right here, so our answer is just 0. Ln, so this would be log base e of e. What is log base e of e equal to? You could put a little 1 right here, and that would be, again, log base e of e is going to be just, this would be equal to 1 the whole way you say it. Well, if I put a 2 out in front of it, well, then it's 2 times 1. So what's my total answer? Just 2. All right, to wrap this up, we only have a few seconds. When we're talking about state the domain, it's what possible x values can be substituted in here. Keep in mind, x can only be you can only take the ln of a positive number. So why don't you try these 2 and bring them up in class, and we'll go over the answers. See you tomorrow.